Welcome to the Deep Dive. We're really glad you could join us again as we explore some fascinating material provided by one of our listeners.
That's right. Today, we're diving into, well, the very heart of chemistry, using these excerpts from a pretty substantial general and inorganic chemistry textbook.
It covers a huge range, from the absolute basics up to some quite specific topics.
Exactly. It takes us right from the tiniest particles, exploring how they behave, how they interact, and how that builds up to the properties we see in the world, even touches on technology.
And our goal here is to sort of guide you through these sometimes complex ideas. We want to pull out the key insights, the really important bits, and show how these fundamental rules of chemistry govern, well, pretty much everything.
Think of it as a journey, starting super small at the atomic level and building up understanding why things are the way they are.
Yeah, and hopefully we'll uncover some surprising facts, maybe some elegant rules you hadn't thought about, and definitely some practical connections. It's kind of a shortcut to being, really well-informed about the chemical world.
There are definitely some aha moments in this material, connecting tiny details to big picture properties.
Okay, let's get started then. Let's unpack this source material and begin right at the beginning.
Sounds good, starting small.
Absolutely. With the fundamental particles, the basic building blocks, your source jumps right into protons, neutrons, and electrons.
The absolute bedrock. Protons give the positive charge in the nucleus and define the element that's the atomic number. Neutrons add mass, no charge, and variations give us isotopes.
Right.
And interestingly, the source makes a point of mentioning that neutrons, like protons and electrons, have this property called spin.
Spin, like spinning tops.
Well, it's a quantum mechanical thing, more like an intrinsic angular momentum. But that little detail, spin, becomes super important later when we talk about analytical methods like NMR, nuclear magnetic resonance. It relies on nuclear spin.
Okay, so file that away for later. And then outside the nucleus, the electrons. The source uses the Bohr model as a starting point here.
Which was really groundbreaking back in 1913. Bohr suggested electrons weren't just whizzing around randomly. They could only exist in specific allowed energy levels, like fixed orbits or shells.
Quantized levels.
Exactly, quantized, numbered 1, 2, 3, and so on. The principal quantum numbers. Not just anywhere in between. It's like steps on a ladder, not a ramp.
So an electron has to be on one step or another.
Precisely. And this immediately explained electron transitions. To jump up to a higher energy level, an electron has to absorb a very specific amount of energy, exactly the difference between the levels.
And then it comes back down.
Right. It's unstable up there. It falls back to a lower level and releases that exact same packet of energy, often as light.
Which explains those sharp lines you see in atomic spectra.
Exactly. The specific colors emitted by elements when they're heated. It was a huge puzzle solved. Bohr's model, even though it's simplified, captured that essential idea. Energy in atoms is quantized.
Building on that, the source moves to how electrons are actually arranged electron configurations, using orbitals like 1s, 2s, 2p.
Right. Orbitals are regions where you're most likely to find an electron. Each orbital holds a max of 2 electrons, and they have to have opposite spins. That's the Pauli exclusion principle.
So the configuration just lists the occupied orbitals and how many electrons are in each, like 1 Seeger, 2 a Seeger.
Yep. Hydrogen, 1 electron, easy, 1 Seeger. Helium, 2 electrons, 1 Seeger.
Oh, seems simple enough.
But the source adds a really nice bit of detail about helium. Why does that second electron go into the 1s orbital? Why not the next level up 2s?
Well, don't electrons repel each other? Putting 2 negative charges in the same small space must cost some energy.
That's exactly the point the source makes. There is an energy cost, the electrostatic repulsion, sometimes called spin pairing energy. The source actually gives numbers for helium.
But really?
Yeah. The energy gain from having an electron in the lower 1s orbital versus the next higher 2s orbital is about 4 megajoules per mole. That's the attraction to the nucleus benefit. But the energy cost of forcing 2 electrons into that same 1s orbital, the repulsion cost, is about 3 megajoules per mole.
So the gain outweighs the cost. 4 MJ saved is better than 3 MJ spent.
Precisely. The overall energy of the helium atom is lower with the Lum-Sacco configuration than it would be with 1s-26. It's a neat little calculation showing how atoms find the lowest energy state by balancing attraction to the nucleus against electron repulsion.
That balance dictates how all the electrons fill up the available orbitals, and that filling pattern leads directly to the periodic table.
Chemistry's ultimate cheat sheet. Its structure is a direct visual representation of electron configurations. The source mentions the history, Reiner, Newland's, Meyer seam patterns.
But Mendeleev was the key figure.
Absolutely. His genius was arranging elements not just by weight, but by their chemical properties, and crucially, leaving gaps for elements that hadn't been discovered yet, even predicting what they'd be like.
Which turned out to be incredibly accurate. A real predictive triumph.
A cornerstone, really. And the modern table shows those broad categories the source mentions. Metals on the left and center, nonmetals on the upper right, and those metalloids or semimetals in between, all grouped by shared characteristics.
And because the table is based on electron structure, properties change in predictable ways as you move across or down. Periodic trends. The source highlights ionization energy first.
Right. That's the energy needed to remove an electron from an atom or ion in the gas phase. And the source talks about successive ionization energies removing the first electron, then the second, then the third.
And it uses lithium as a key example.
Perfect example. Lithium has 3 electrons, 1 SSO2 S scissors. Removing that outer 2's electron, the first ionization, takes 0.52 mJ-mol. Pretty low, makes sense for an alkali metal that likes to form a +1 ion.
Okay.
But then look at the second ionization energy, removing an electron from Leo. It jumps to 7.4 mJ-mol. And the third, removing the last electron from Rio, is 11.8 mJ-mol.
Wow, that jump from the first to the second is huge, like more than 10 times the energy.
That's the crucial point the source is making. Yes, you expect it to take more energy each time because the positive charge is increasing, but that jump is massive. The reason goes right back to the electron configuration.
It's because the second electron is from that inner one's shell.
Exactly. The first electron was the outer 2's electron, further out, shielded by the 2 1's electrons. The second electron is a 1's electron. It's much closer to the +3 nucleus, and now it's only being shielded by the other 1's electron. It feels a much stronger pull, a much higher effective nuclear charge.
So it's held way more tightly, less shielded and closer in.
Precisely. It vividly shows the difference between valence electrons and core electrons. That second to third jump for lithium is also significant, but not nearly as dramatic because you're still removing a tightly held 1's electron.
Okay, that makes sense. Then there's electron affinity.
This is the energy change when a gas phase atom gains an electron. The source refers to a chart showing trends generally. Elements on the right, like halogens, have favorable negative electron affinities. They like gaining an electron to complete their outer shell.
But there's a catch mentioned in the source.
Yeah, an important one. These values are for isolated atoms in the gas phase. They indicate a tendency, sure, but they don't always predict how stable a compound will be in a real chemical environment. Compound stability depends on many factors. Lattice energy for ionic solids, bond strength, solvent interactions. It's just one piece of the puzzle.
Got it. And the third trend, electronegativity.
This one's about how strongly an atom pulls on electrons within a chemical bond. It's not about gaining an electron from nowhere. It's about the tug of war for shared electrons between bonded atoms.
And the key thing is the difference in electronegativity.
Exactly. A big difference means one atom pulls much harder, leading to a polar bond or even an ionic bond if the difference is large enough. The source uses HCl, hydrogen chloride, as an example.
Chlorine pulls harder than hydrogen.
Much harder. So the shared electrons spend more time near the chlorine. This creates a permanent separation of charge, a dipole moment. The chlorine end is slightly negative, delta minus, and the hydrogen end is slightly positive, delta plus.
Okay, so these properties, ionization energy, electron affinity, electronegativity, they all stem from the atom's structure and electron arrangement. And they really dictate how atoms are going to interact and bond.
They set the stage for chemical bonding, which is exactly where the source goes next.
Right, so how do these atoms actually connect?
The source lays out the main types. You've got your ionic bonds, big electronegativity difference, electron transfer, positive and negative ions sticking together electrostatically in a lattice.
Like table salt, sodium chloride.
Classic example. Then covalent bonds, smaller electronegativity difference. Atoms sharing electron pairs to get more stable configurations, typical for nonmetals bonding.
Like water, HO.
Yep. And then there's metallic bonding. The source explains this using the electron gas or electron C model. It's a simple picture, but quite useful.
How does that work?
You imagine a grid, a lattice of positive metal ions, and the outermost valence electrons are detached, essentially, and free to move throughout the entire metal crystal, like a sea or gas of electrons bathing the ions.
And that explains why metals are shiny and conduct electricity.
It does. Those mobile electrons can easily carry electrical current. They can also transfer kinetic energy efficiently, which is why metals conduct heat well. And their interaction with light-absorbing and re-emitting photons is what gives metals their characteristic luster and makes them opaque.
The source also mentioned why heating a metal decreases its conductivity.
Right. Using this model, as you heat the metal, the positive ions in the lattice vibrate more intensely. These vibrations disrupt the smooth flow of the electron sea, scattering the electrons and making it harder for them to move through, hence higher resistance, lower conductivity. It's a simple model, as the source notes, but captures the essence.
Okay, diving deeper into covalent bonds, there's the famous octet rule.
The general guideline, yeah. Atoms tend to bond in ways that give them 8 valence electrons, like the noble gases. Well, except for hydrogen, which aims for 2.
But it's just a guideline, right?
Yeah.
The source mentions exceptions like PFU and SFURO.
Oh yes, plenty of exceptions, especially further down the periodic table. Phosphorus pentafluoride, PFEOs, and sulfur hexafluoride, SFURs, are examples of hypervalent molecules. The central atom seems to have more than 8 electrons around it, 10 for P and PFUs, 12 for S and SFU if you draw simple single bonds.
So the octet rule doesn't strictly apply there.
Well, you can draw formal resonance structures with double bonds or charge separation that technically satisfy the octet rule for the central atom, but the source points out these often don't match reality very well. For instance, in PFU, all 5 PF bonds are experimentally found to be pretty much identical.
Which wouldn't be the case if some were single and some were double bonds.
Exactly. So while the octet rule is a useful starting point, these expanded octet cases are better described using molecular geometry or more advanced bonding theories. They show the limitations of the simple rule.
And predicting the actual 3D shape of these molecules, that's where VSEPR comes in. Valence shell electron pair repulsion.
VSEPR, a wonderfully useful and intuitive model. The core idea is simple. Electron pairs around a central atom repel each other, whether they're bonding pairs in a chemical bond or lone pairs, not involved in bonding. They're all regions of negative charge, and they want to get as far away from each other as possible.
So they arrange themselves in space to minimize that repulsion.
Precisely. And that arrangement of electron pairs dictates the overall geometry of the molecule. It leads directly to shapes like tetrahedral for methane, CH, with 4 bonding pairs, or trigonal planar for BFF with 3 bonding pairs.
The source also talks about rarer, more complex shapes, like for molecules with 7 things attached. MX-URG.
Yeah, it mentions these are uncommon. You usually need a large central atom and small, highly electronegative ligands like fluorine. The source says there are 3 main possibilities for MX geometry that are energetically very close: pentagonal bipyramid, capped trigonal prism, and capped octahedron.
And there are real examples for each.
Apparently so. IF is pentagonal bipyramidal. The ion NBF-UR is a capped trigonal prism. And X-UR in the gas phase is thought to be a capped octahedron, although it's a bit floppy. It shows that sometimes the energy landscape for molecular shapes can be quite complex with multiple stable or near-stable arrangements.
VSTR isn't just about the basic shape, though. The source highlights how it predicts subtle differences in bond angles, too.
Yes, this is where it gets really interesting. It gives 2 great examples. First, the phosphorus trihalides. PS, PCS, PS, PS.
What happens to the angles there?
The XPX bond angle actually increases as you go from F to I. 98 degrees for PSS, 100 degrees for PSLOs, 101 degrees for PBROs, and 102 degrees for PS.
Why is that?
The source explains it using electronegativity. Fluorine is very electronegative. It pulls the bonding electrons in the PF bond strongly towards itself, away from the phosphorus. This means the PF bonding pair takes up less space near the phosphorus atom. This allows the lone pair on phosphorus to push the PF bonds closer together, giving a smaller angle. Iodine is much less electronegative. The Pi bonding electrons are shared more equally, take up more space near P, repel the lone pair more strongly, and push the bonds further apart, leading to a larger angle.
That makes sense. And the other example,
Yeah.
the group 16 hydrides, HOHS.
Right. Water, hydrogen sulfide, HS, hydrogen selenide, HA, hydrogen telluride, HE. These are all bent molecules with 2 lone pairs on the central atom. Here, the HXH bond angle decreases down the group, 104.5 degrees for water, then 92 degrees, 91 degrees, down to 89 degrees for H.
So the opposite trend. Why?
This time, the explanation focuses more on the lone pairs and the central atom's electronegativity. Oxygen is highly electronegative. It pulls its lone pairs in close, making them take up relatively less space compared to the bonding pairs. This allows the HOH bonds to spread out more. As you go down the group, the central atom, SCT, gets larger and less electronegative. It holds its lone pairs less tightly, they spread out more, become more diffuse, and exert a greater repulsion on the bonding pairs, squeezing the HXH angle shut.
Wow. Those are really fine details that VSTAR can predict just based on fundamental properties like electronegativity.
It's surprisingly powerful for such a simple model.
Yeah.
Okay, so from individual molecules, the source then looks at how things connect on a larger scale. Covalent networks are first.
Like diamond or silicon dioxide, quartz.
Exactly. These aren't made of separate little molecules. Instead, every atom is covalently bonded to its neighbors in a continuous network extending throughout the entire crystal. It's like one giant molecule.
And that structure has huge consequences for properties.
Absolutely. To melt or boil diamond or cyauro, you have to actually break those strong covalent bonds, which takes a massive amount of energy, hundreds of kilojoules per mole. That's why diamond melts around 4,000 degrees C and quartz around 1,700 degrees.
Makes them super hard too, right?
Incredibly hard. Diamond's the hardest known substance, and generally insoluble because you'd have to break down that whole network to dissolve it. It's a completely different bonding situation compared to, say, solid water ice, where you only need to overcome weaker forces between HUO molecules to melt it.
Speaking of forces between molecules, intermolecular forces.
Right. These are much weaker than covalent or ionic bonds, but they're critical for understanding properties like boiling points, melting points, and solubility of molecular substances.
The source uses the group 14 hydrides as an example. CH.
Methane, CH, silane, cyane, shenane, stannane, SNH. Their boiling points increase steadily as you go down the group. Negative 162 degrees C, negative 112 degrees, negative 88 degrees, negative 52 degrees.
Like.
It comes down to the size and number of electrons. As the molecules get bigger going down the group, their electron clouds become larger and more easily distorted or polarized. This leads to stronger, temporary, fluctuating dipoles known as London dispersion forces. More electrons mean stronger dispersion forces, which means more energy, a higher temperature, is needed to pull the molecules apart into the gas phase.
And we also have permanent dipoles, like in HCl.
Yes, if a molecule is polar due to electronegativity differences, like HCl, then there's also an attraction between the permanent partial positive charge on one molecule and the partial negative charge on another. These dipole forces add to the intermolecular attraction.
Okay. The source then takes a slightly different angle, looking at molecular symmetry.
Symmetry is a really fundamental concept in chemistry. Molecules can have various symmetry elements, rotation axes, mirror planes. The source specifically mentions the inversion center, symbol I.
An inversion center. What is that exactly?
A molecule has an inversion center if you can take any atom, draw a straight line through the geometric center of the molecule, and find an identical atom at the same distance on the exact opposite side.
Can you give some examples?
Sure. The source lists ethi, acetylene, CH, benzene, CH, and the trans form of a diazine, N-euros, as having inversion centers. Molecules like water, HO, methane, CH, and cystiazine do not have one. The source also gives a useful tip. Molecules with an even-fold main rotation axis, like C, Ca, and a mirror plane perpendicular to that axis will always have an inversion center. Xenon tetrafluoride, XE, is a good example, square planar structure.
And this geometric property, symmetry, it actually matters.
Oh, definitely. Especially for understanding molecular vibrations and how we study them using spectroscopy. Molecules aren't rigid statues. Their atoms are constantly vibrating, stretching bonds, bending angles.
And the number of ways they can vibrate depends on the number of atoms.
Yeah. For a nonlinear molecule with n atoms, there are 3 and 6 fundamental vibrational modes. For a linear molecule, it's 3 and 5. The source mentions the types. Stretching vibrations, changing bond lengths, and bending or deformation vibrations, changing bond angles.
It uses water as an example.
HO is nonlinear N3, so it has 3336 equals 3 fundamental vibrations. The source lists them: a symmetric stretch, an asymmetric stretch, and a bending mode, each with a specific frequency.
And this connects to IR and Raman spectroscopy.
Directly. Infrared IR spectroscopy works by shining infrared light on a sample. A molecule will absorb IR light at a frequency corresponding to one of its vibrations if that vibration causes a change in the molecule's overall dipole moment. If the dipole moment doesn't change during the vibration, it's IR inactive.
And Raman.
Raman spectroscopy works differently. It involves scattering light off the molecule. A vibration is Raman active if it causes a change in the molecule's polarizability, basically. How easily the molecule's electron cloud can be distorted by the light's electric field.
And here's where symmetry comes back in with that alternative Verbat rule.
The mutual exclusion rule. It's a fantastic consequence of symmetry. For any molecule that possesses an inversion center, a vibration that is IR active must be Raman inactive, and any vibration that is Raman active must be IR inactive. No vibration can be active in both spectra.
Wow. So just by looking at whether the IR and Raman spectra have peaks at the same frequencies, you can tell if the molecule has an inversion center.
Exactly. It's a powerful diagnostic tool based purely on the molecule symmetry. If the spectra are completely different, the molecule must have that center of symmetry.
Okay, that's really neat. So we've gone from atoms to bonds to shapes to vibrations. Let's look at how these things play out on a larger scale, bulk properties like solubility and reactions in solution.
Right. Connecting the microscopic details to macroscopic behavior, solubility is a great place to start. How do things dissolve, like salts in water?
It's about water molecules interacting with the ions, right?
Fundamentally, yes. Water is polar. The negative oxygen end is attracted to positive cations, and the positive hydrogen ends are attracted to negative anions. This is the ion-dipole interaction. If this attraction is strong enough to overcome the energy holding the ions together in the crystal lattice, the salt dissolves.
And the source contrasts different types of metal ions, alkali metals versus transition metals.
It does. Alkali metal ions like Na or Co have a +1 charge and are relatively large, so their charge density is low. The ion-dipole interaction is strong enough to dissolve them, but the water molecules aren't usually super tightly bound.
But transition metals are different, like iron or copper ions.
Often, yes. They tend to be smaller and can have higher charges, +2, +3, leading to a much higher charge density. The interaction with water is so strong, it's often better described as forming coordinate covalent bonds. The water molecules act as Lewis bases, donating electron pairs to the metal ion, which acts as a Lewis acid. The source gives FH0 as an example, 6 water molecules chemically bonded to the iron ion in an octahedral arrangement. This complex ion exists as a distinct entity in solution.
The difference in interaction helps explain solubility differences. The source compares potassium halides and silver halides.
A classic comparison. Potassium halides KF, KCl, KBr, Ki are all very soluble. They're highly ionic, but silver halides AgCl, Agr, Agi are famous for being insoluble. Silver fluoride, AgF, is soluble, though.
Why the difference for silver?
The source points to increased covalent character in the AgCl, AgBr, and Ag bonds. Because silver is less electropositive than potassium and the larger halides are more polarizable, there's more electron sharing. This partial covalency reduces the effective charges on the ions, weakening the ion-dipole interaction with water, making it insufficient to overcome the lattice energy.
But AgEF is soluble because fluorine is so electronegative.
Exactly. The Ag bond has the most ionic character among the silver halides. More ionic means stronger interaction with water, hence solubility. It fits nicely with concepts like Fedesian's rules mentioned in the source.
Solubility isn't always fixed, though. The source mentions complex formation can increase it.
Right, this is about shifting equilibria. Take insoluble AgCl. It dissolves slightly. AgCls plus click A. If you add extra chloride ions, say from NeCl, the chloride can react with the few Ag ions present to form soluble complex ions, like the linear AgL.
And that pulls more AgCl into solution.
Yes, because you're removing AGO from the initial equilibrium, Le Chatelier's principle says the equilibrium shifts right, dissolving more solid AgCl to replace the removed AGO. The source gives another example. Insoluble QCN dissolving in potassium cyanide, KCN solution, because stable, soluble QCNO complexes are formed.
The source mentions the solubility product, Kl, for quantifying this.
Kl is the equilibrium constant for the dissolution process. For AgCl, Kl equals AgOClO. For something like Kaz, which dissolves to give KAGO and 2 ions, Kl equals Ko. You can calculate the molar solubility from Kl, remembering the stoichiometry. But, as the source notes, if other equilibria are involved, like complex formation, you need more than just the Kl expression. You need a system of equations, including things like the electroneutrality condition. Total positive charge must equal total negative charge.
For dissolving to reacting acids and bases in water.
The source uses the Brunstad-Lowry definition. Acids are proton aid donors, bases are proton acceptors. Water itself is key because it can act as both its amphoteric.
And this leads to the leveling effect in water.
Exactly. Because water can accept or donate photons, it sets limits on acid-base strength in aqueous solution. The strongest acid that can exist significantly is HO, hydronium. Anything stronger, like HClO mentioned in the source, reacts completely with water to form HO. Similarly, the strongest base is OA, hydroxide. Anything stronger reacts completely with water to form OA. Water levels all very strong acids and bases down to HO and OA.
Then we have pH and pOH for measuring acidity-basicity.
Right, the logarithmic scales. pH equals NaS log A, pOH as log U. And in water at 25 degrees C, pH plus pOH of 14. The source gives quick examples for calculating pH of strong acids, like HCl, and strong bases, like NaOH, where dissociation is complete.
But many acids and bases are weak.
Meaning they only partially react with water. This is an equilibrium described by the acid dissociation constant, Ks, or the base dissociation constant, Kb. Larger Ks or Kb means a stronger, but still weak, acid or base.
And we track these pH changes in experiments using indicators.
Acid-base indicators. They're typically weak organic acids themselves, where the acid form, AS-uracil, and its conjugate base form, indo, have different colors.
So the color depends on the pH.
It depends on the ratio of Hin to Indo, which is directly controlled by the pH according to the equilibrium Hin plus Indo. The source notes that we typically perceive the color change over a range of about 2 pH units centered around the indicator's own pKs value, where pKs equals log Ks. So the change happens roughly when pH is log so 1.
And choosing the right indicator is vital for titration.
Absolutely critical for accuracy. In a titration, you're finding the equivalence point where moles of acid equal moles of base. The pH at that equivalence point isn't always 7. For example, titrating a weak acid like acetic acid with a strong base like NaOH, the equivalence point is basic, pH 7, because the acetate ions react with water.
So you need an indicator that changes color in that basic pH range.
Exactly. The source uses this example. Methyl orange, pKs 3.7, would be useless. It would change color way too early. Phenolphthalein, pKs 9, is perfect because its color change, colorless to pink, happens right around the sharp pH jump at the basic equivalence point of that specific titration. Using the wrong indicator gives you the wrong result.
Good point. Okay, shifting gears again to another major reaction type, redox.
Reduction, oxidation, electron transfer reactions. The source starts with oxidation states formal charges assigned based on electronegativity rules, pretending bonds are ionic.
Like in HCl, Cl is minus I, H is plus I. In water, O is negative D, I, H is plus I.
Right. Oxidation is an increase in oxidation state, losing electrons. Reduction is a decrease, gaining electrons. They always happen together. Then the source introduces standard electrode potentials, ER.
These numbers from tables that tell you how much something wants to be reduced.
Under standard conditions, 1M, 1 at Tale, 25 degrees, yes. A more positive ER means a greater tendency for reduction. It's a stronger oxidizing agent. But these are just standard reference points. The actual potential depends on concentration, which is described by the Nernst equation.
So the potential isn't fixed.
Nope. The Nernst equation shows how potential varies with the ratio of reactant and product concentrations. The source has a neat example. Making a battery just by connecting two identical half cells, say a GOAG, but with different silver ion concentrations in each.
You get voltage just from a concentration difference.
You do. The Nernst equation predicts a potential difference, driving a current as the system tries to equalize the concentrations.
The source also uses potentials to talk about stability of different oxidation states, using Frost diagrams.
Frost diagrams are a great visual tool. They plot the relative free energy of different oxidation states of an element, usually scaled by the oxidation state number, versus the oxidation state itself. The lower an oxidation state is on the diagram, the more stable it is.
And the shape tells you things.
Yes. If a point lies above the line connecting its neighbors, that oxidation state is unstable towards disproportionation reacting with itself to form the states on either side. If it lies below in a valley, it's stable against disproportionation. The source mentions looking at the third metals diagram. Ti 0 is low, good reducing agent. Stability generally increases across the series. Highest oxidation states become less stable later on.
It mentions manganese and copper specifically.
Right. For manganese in base, the diagram shows MnO, MnIV, is quite stable, sitting in a minimum. For copper in acid, the diagram shows Cu lies above the line connecting C0 and Cuo, indicating Cu is unstable and tends to disproportionate into copper metal in Cu ions, which it does in water.
And a practical redox example, potassium permanganate, KMnIO.
A common lab reagent, it's intensely purple. In acid, the permanganate ion, MnOO, is a strong oxidizing agent, getting reduced usually to the nearly colorless Mn ion.
And that color change is useful.
Extremely. It acts as its own indicator in redox titrations, say you're titrating iron. As you add the purple KMnOO, it reacts with Feol and turns colorless. The instant all the Feol is gone, the next drop of KMnOO stays purple, signaling the endpoint. The source mentions using it for oxalic acid and iron determination.
Very clever.
Yeah.
Okay, we've covered fundamentals, bonding, shapes, properties, reactions. Now for some specific interesting case studies from the source material, seeing the principles in action.
These are great. The Ka-UO versus SiO comparison is a classic.
Right. Carbon and silicon are in the same group, but Ka-UO is a gas, SiO is a quartz, a hard solid. Why such a huge difference?
It boils down to bonding preference with oxygen. Carbon loves forming double bonds. The source gives the CO double bond enthalpy as 804 kilojmol, very strong, much stronger than two CO single bonds at 358 kilojmol each. So energetically, it's favorable for carbon to form discrete OCO molecules. These molecules only interact weakly, hence it's a gas.
But silicon doesn't do that.
No. The SiO single bond is unusually strong, 465 kilodalmol, stronger than a CO single bond. The source mentions this is due to some partial double bond character involving oxygen lone pairs interacting with silicon orbitals and negative hyperconjugation. This strong single bond, combined with flexibility, wide SiO-Si angles, favors forming an extended 3D network where each Si is bonded to 4 O's, and each O bridges 2 Si's.
So discrete molecules versus a giant network.
Exactly. And breaking that network takes huge energy, leading to the high melting point and hardness of SiO, contrasting completely with the weak forces between Cu molecules. A fundamental bonding difference leads to drastically different materials.
Another intriguing case, the trouble with making arsenic chloride, ask Killa2.
Yeah, the source notes that PClEO and SbCl, the neighbors above and below arsenic, are pretty stable, so chemists expected AsClO to exist and be similar.
But it was really hard to make.
For a long time, yes. People tried and failed. The source credits case separate for finally succeeding in 1976 under very specific cold conditions. Reacting ascols with liquid chlorine in UV light at -105 degrees C. And even then, the product ascol is unstable, decomposing around -50 degrees C.
So why is it so much less stable than PCO or SbClO?
The explanation connects back to arsenic's position in the periodic table right after the first row of transition metals, the third elements. The source points out that this instability of the highest oxidation state, plus V for A's, is typical for elements in that row like Ga, J, C, Br, compared to their lighter or heavier relatives.
It's because of those d electrons.
It seems so. The third electrons, which were filled in the preceding transition series, are apparently not very good at shielding the outer 4s and 4p electrons from the increasing nuclear charge.
Meaning those outer electrons feel a stronger pull from the nucleus than you might expect.
Especially the 4s electrons. So while arsenic can lose its 3 4p electrons relatively easily to get to the +3 state, removing the 2 4s electrons as well to reach the +V state is energetically much more costly for arsenic and its neighbors Go, G, etc. than it is for phosphorus, which only has 2p electrons shielding its 3s3p, or antimony, where shielding by 4b electrons is maybe more effective, or other factors dominate.
Wow. So a subtle effect of electron shielding has a major impact on the stability of a whole compound.
It's a fantastic link between subatomic structure and macroscopic chemical stability. The source also looks at aluminum chemistry, which shows interesting variety.
Aluminum halide, AlSu.
Is ionic, right?
Yes, forms an ionic lattice, typical for fluorides of less electronegative metals. Contrast that with Bs above it, which is a covalent molecule. The source suggests the large electronegativity difference favors ionic allyls, while the very high charge density of the tiny B ion favors polarizing the fluoride ions and forming covalent bonds in BFS.
But alkys are different again. They are. They don't exist as simple AlXU molecules under normal conditions. Instead, they form dimers, Al-Uro. This structure persists in the solid for chloride, liquid, and gas phases, and even in nonpolar organic solvents.
Why the dimer?
The monomer Al-Urus is electron deficient. Aluminum only has 6 valence electrons around it. Unlike boron, which can get some help from pi bonding with halogens, the Alex distance is too large for effective pi bonding. So aluminum finds another way to satisfy its octet.
By pairing up.
Exactly. Halogen atom on one AlXU unit uses a lone pair to form a coordinate bond to the electron-deficient aluminum atom on another unit. This forms 2 bridging halogen atoms linking the 2 aluminums, creating the Al-Uro dimer. In this structure, each aluminum achieves an octet. It's a classic Lewis acid, Al-Lewis base bridging halogen interaction.
And anhydrous Al-Urus reacts vigorously with water.
Oh yeah, very exothermic, releases HCl gas. The source gives the simple equation Al-Tir plus 3H Urus plus 3HCl. It shows how reactive that electron-deficient aluminum center can be.
The source also connects chemistry to everyday life and health. Sodium chloride.
Not just table salt, a huge industrial chemical over 150 million tons a year globally, the source says. It comes from ancient dried seas, mined underground or by dissolving it with water, solution mining.
And the taste substitute fact.
Right. KCl is often used, but apparently needs additives because pure KCl doesn't taste quite the same as NaCl.
Then selenium. Essential but tricky.
Very much so. It's a vital trace element for enzymes like selenoproteins that handle oxidative stress, but the source stresses the very narrow window between deficiency, 0.05 mg/kg in diet, causing problems like Keyshawn disease, and toxicity, 5 mg causing chronic poisoning. A real dose makes the poison example.
And sodium nitrite, mano, the food additive E250.
Used in curing salts for meat, max more 0.5%. Its main job, according to the source, is inhibiting dangerous bacteria, especially Clostridium botulinum, which causes botulism.
But it also affects the color.
Yes, that's the secondary purpose mentioned. It helps keep cured meats like ham and bacon pink red. Nitrite forms nitric oxide, NO, which binds to the iron in myoglobin, preventing it from oxidizing to the brownish metmyoglobin form and preserving that characteristic cured meat color.
Amazing. Okay, finally, the source links these principles to modern tech. Lithium-ion batteries.
Briefly mentioned, the core idea is lithium-ions moving between anode and cathode during charge-discharge, with redox happening at the interfaces. Speed is limited by ion movement. Manufacturing involves coating materials like graphite and metal oxides onto foils. It's all applied electrochemistry.
And optical fibers. How is chemistry involved there?
It's crucial. These fibers transmit light pulses carrying information. They're made of ultra-pure glass, mostly SiO, that network solid we discussed. The key, the source explains, is precisely controlling the refractive index of the glass.
Why is that important?
The refractive index dictates how fast light travels. By making the core of the fiber have a slightly higher refractive index than the outer layer, the cladding, light is guided along the core by total internal reflection. To send data fast without distortion, you need a very specific profile of refractive index across the core. This is achieved by carefully adding controlled amounts of other oxides, like germanium dioxide, GeO, to the SiO.
How do they get that precise control?
The source mentions chemical vapor deposition, CVD. Gases like Cicro and GGRO are reacted inside a tube to deposit layers of SiO and GRO. By carefully controlling the gas mixture over time, they build up the core material layer by layer with exactly the right composition profile to get the desired refractive index gradient for high-speed communication.
That's incredible. Directly connecting the chemistry of silicon oxides to global internet infrastructure.
It really shows how fundamental chemistry underpins advanced technology.
Okay, fantastic examples. We covered the building blocks, bonding, shapes, properties, reactions, and these case studies. Let's finish by touching on some of the tools chemists use, as mentioned in the source. NMR spectroscopy.
Nuclear magnetic resonance. Hugely powerful for figuring out molecular structures. As we mentioned way back, it relies on the fact that some atomic nuclei have spin. Not all do, like carbon-12 or oxygen-16, but key ones like hydrogen-1 protons, carbon-13, fluorine-19, phosphorus-31 have spin-12, which is ideal for NMR.
And the spin interacts with a magnetic field.
Right. In a strong magnetic field, these nuclear spins align either with the field, lower energy, or against it, higher energy. The energy difference between these two states is tiny, corresponding to radio wave frequencies, typically hundreds of megahertz.
So you zap the molecule with radio waves.
Essentially, yes. Modern FTNMR uses a pulse of radio waves to excite the nuclei. As they relax back down, they emit signals at their specific resonance frequencies. And here's the key. The exact frequency depends very sensitively on the electron cloud around that nucleus, its chemical environment. Nearby atoms also influence the signal through spin-spin coupling.
So the NMR spectrum is like a detailed map of the molecule structure.
Exactly. Different signals for chemically different nuclei. The position, chemical shift, tells you about the environment, and the splitting pattern tells you about neighbors. It's indispensable. The source also briefly nods to isotope effects influencing things like vibrations or NMR shifts.
And finally, a quick look back at thermodynamics in practice with the Van 't Hoff equation.
Ah, yes. N/K Nash AH degree RT plus Sand's degree. It connects the equilibrium constant K to enthalpy change, entropy change, and temperature, T.
What's the practical use?
It allows chemists to predict how changing the temperature will affect the position of equilibrium and therefore the maximum possible yield of a reaction. If a reaction gives off heat, exothermic, 8 degrees negative, raising the temperature actually reduces the yield at equilibrium. If it absorbs heat, endothermic, CH2 positive. Raising the temperature increases the yield. The source mentions using it to calculate the temperature needed for a decomposition reaction, like making lime from limestone, to become favorable.
So it helps optimize reaction conditions.
Precisely. It connects fundamental energy changes to practical control over chemical processes.
Wow, what a journey through this material. From electrons and orbitals to why salt dissolves, why ASCOE is unstable, how NMR works, and how optical fibers function.
Yeah.
It really all links together.
It does. Chemistry provides this underlying logic, these rules that connect the unimaginably small to the tangible world and the technologies we use. It's all governed by these principles.
It gives you a completely different way of looking at things. And maybe that's a final thought for you, our listener. Think about the stuff around you right now. Your phone battery, a plastic bottle, the paint on the wall, the air you're breathing, maybe even just a glass of water.
Every single one is a product of these chemical principles playing out bonding, structure, forces, energy changes, the way materials behave, the way reactions happen. It all comes back to this fundamental chemistry.
Can you start spotting those connections yourself? Seeing the rusting of metal, the cooking of food, the setting of glue, seeing them as demonstrations of electronegativity, redox reactions, bond formation, intermolecular forces.
It really does open up a new perspective on the world. We hope this deep dive into your source material has been enlightening and maybe made some of these complex ideas feel a bit more accessible.
It's been fascinating to explore it with you. Thanks so much for providing the material and for joining us on the deep dive.